Okay, hey guys, it's time to learn L'Hopital's rule. Here we go. L'Hopital's rule to find limits of indeterminate forms. Indeterminate forms. Here's what I mean by a limit of an indeterminate form. One indeterminate form is infinity over infinity. Tell me, what's infinity over infinity equal to?
1.
You'd think,
Oh.
but what if I did this? The limit as x approaches infinity of 2x plus 5 over x.
It's infinity.
Plus 7. Okay? What's the numerator? Infinity, right? Because you stick infinity, or 2 infinity plus 5. What's the denominator?
Infinity.
But what's this limit going to be equal to?
2.
2, right? Beautiful. So I have infinity over infinity, because they're both infinity. They're both infinitely large, but we know that that limit ends up equaling 2. But what if I have this? The limit as x approaches infinity of 3x plus 9 over x minus 1. What's that limit equal to? 3, right? The numerator is infinity, the denominator is infinity, but that's equal to 3. So that's why I say infinity over infinity is an indeterminate form. If someone gives you infinity over infinity and asks you what's it equal to, your answer is it depends. It depends what sort of infinity I have here, and it depends what sort of infinity I have here. Hey, you guys tell me, the limit as x approaches infinity of e to the x power over x. What do you suppose that's equal to?
Shoot.
Well, I'll tell you, the numerator's infinity, the denominator's infinity, but guess what? Who's a bigger infinity? Yeah, the numerator. In fact, the numerator is infinitely bigger than the denominator, right? Infinitely bigger. And so the answer ends up being infinity. So we need some way algebraically to determine what infinity over infinity is. Because the fact is, a priori, we don't know. You know, it's indeterminate. Who knows? It depends. And the same sort of thing happens with 0 over 0. What if I have this? I mean, right off the bat, what's 0 over 0 equal to?
Undefined.
Undefined, okay. I tell you it's equal to 1. Right? I mean, it's the same thing, 0 over 0. Anything over anything is equal to 1, you'd think. But here, let's do this. The limit as x approaches 2 of x minus 2 over x squared minus 4. What's that equal to? Well, what would you have me do?
Plug in 0.
Yeah, okay, I can take my calculator and plug in 2. The problem is my calculator will say undefined.
Oh, yeah.
But there's a way I could get close. Instead of plugging in 2, what could I plug in? Anyone thinking of 1.9999999? That'll work. You could plug 1.99999 in your calculator and you'd get close to the answer, or 2.000001 and you get close to the answer, and that would be fine. But we want to have a method where we're not depending on technology to get the answer. And Daniel, what were you going to say? Were you going to recommend something?
I was going to say you could simplify it.
Oh, simplify it. Let's simplify it, because I like to simplify things, like simplifying my life. I like to do that. Get rid of a bunch of stuff I don't need. Like in this case, we don't need the x minus 2's. Boop, boop. And so I stick in a 2 and I get 1/4. Does that mean that the limit of 0, does that mean 0 over 0 is always equal to 1/4? No, it depends. I could give you a bunch of other stuff here where it could be anything I want it to be. Okay? So that's why 0 over 0 is an indeterminate form. Alrighty? So I am now going to teach you L'Hopital's rule to find these two indeterminate forms. Here it comes. L'Hopital's rule. And I'm not going to prove it, I'm just going to tell you this is what it is. Okay? Just a second, we got a little message. Thank you. Angel,
Where are you going?
go to C7 at some point.
Okay.
She says it's important, but I would ignore that.
You're in trouble.
Okay. If the limit of f of x over g of x
From
results
7 to 12.
in 0 over 0 or plus and minus infinity over plus or minus infinity
Oh, no, that's the date.
form, then we get to do what we always wish the quotient rule allowed us to do. I get to do this. Then the limit of f of x over g of x ends up equaling the limit of f prime of x over g prime of x. That is, we get to just take the derivative of the top and the derivative of the bottom, and then we plug it in again. Let me show you an example. What if I have the limit as x approaches 0 of e to the 2x minus 1 over x?
Listen.
Less.
Well, the first thing we do is check, is it one of those indeterminate forms, 0 over 0 or infinity over infinity? Is it this guy or this guy? That's our first thing we check. You tell me, is this one of those two indeterminate forms?
Yeah.
Good. Are you guys okay with that? As x approaches 0, I get 1 minus 1, which is 0. And as x approaches 0, I get 0 in the denominator, right? So this is 0 over 0 form. And we have a special symbol we use when we find that we have 0 over 0 or infinity over infinity form, because that tells me I can use L'Hopital's rule. And that special symbol is a happy face.
Are you serious?
No, I just made that up. But it makes me happy when I can use L'Hopital's rule. So there it is. Okay, so let's go ahead and do L'Hopital's rule. Tell me, what does the numerator become?
2e to the power of 2x.
Thank you very much, Daniel, you're so smart. 2e to 2x, and what does the denominator become?
1.
Good. Now, this is no longer indeterminate. If I just stick in 0, what do I get?
You get 1.
No.
Two.
I mean 2.
Yeah, you guys okay with that? I get 2, and there's my answer. So the limit of this indeterminate ratio actually ends up being 2. You guys okay with that? Okay? Hey, you guys ready to do one on your own?
Sure.
Good, that's what I like to hear. So here comes the limit. Here we go, example number 2. The limit as x approaches negative infinity of x squared over e to the negative x power. The first thing you must do is verify, is it one of these two forms? Because if it's not, you don't get to do L'Hopital's rule.
No. It's not.
What's the numerator?
X squared e to the x.
No, but right now it's a fraction. So that's good. We need it to be a fraction. This is a fraction. When I stick negative infinity into the numerator, what do I get? Infinity. When I stick negative infinity in for x, what do I get?
Really big.
Infinity. True enough. And so are you guys okay that this is actually infinity over infinity form? Which, you know what I get to say?
Happy face.
Happy face. So I'd like you please to complete this problem. Take the derivative of the top and bottom.
It's a negative exponent. Mr. Shana,
Mm-hmm.
if it's a negative exponent though, aren't you supposed to raise it to the top?
No. I mean, yes, but no. Because we need it to be a fraction in order to use L'Hopital's rule. So actually, I'd be working against myself.
Well, I understand that,
You see what I mean? Yeah, but yes, ordinarily, sure. So the answer, yes, Andrew, is yes. Ordinarily, yes. But not now. Okay, so I took the derivative. So I stick in negative infinity to the top, and I get negative infinity, right? 2 times negative infinity is negative infinity. I stick in negative infinity to there, and I get negative infinity. Oh my gosh, what am I going to have to do?
Another derivative.
Simplify or take the derivative again.
Thank you. I have to do L'Hopital's again, so that make me even happier. Okay, so please go ahead and do L'Hopital's rule again. And sometimes you'll have to do it multiple times before you finally get to an answer. I should put equal signs there. So now what are you getting as your answer?
0.
Yeah, 0. Now this isn't indeterminate anymore. I got 2 over infinity, and 2 over a million, billion, trillion is approximately 0. You see? So that limit is going to be 0. Okay, so that's L'Hopital's rule. L'Hopital's rule says I need to have it to be 0 over 0 or infinity over infinity form, then I get to get the derivative of the numerator and denominator. And it's all good. But here's the problem. Can I erase this?
Yeah.
Here's the problem. There are many other indeterminate forms besides 0 over 0 and infinity over infinity. And I'd like to introduce some of those additional indeterminate forms to you now. Other indeterminate forms. Okay. Here, how about infinity minus infinity? Tell me, what's infinity minus infinity?
0.
You would think 0, but the fact is it depends on how big the infinities are, right? If I have the limit as x approaches infinity of 2x minus x, right? That's infinity. That's infinity. But in this case, what's my answer going to be?
2? Oh, 1.
No, it's going to be the limit as x approaches infinity of, what does that simplify to? Yeah, x. So what do I get? Infinity, right? I mean, essentially it's saying if I have infinity minus infinity, but this infinity is really, really way bigger than that infinity, then I still get infinity. But what if I have this? The limit as x approaches infinity of x minus the square root of x squared plus x. Do that on your graphing calculator, plug in a really, really big number like a billion. You don't have to do it, just trust me. You plug in a million or a billion or a trillion, and you know what you start getting really, really close to? Negative a half. Yeah, it ends up being negative a half.
Yeah.
So you get this weird situation. When someone asks me, what's infinity minus infinity? The answer is, hey, it depends, right? It depends how big your infinities are. That's one indeterminate form. There's another indeterminate form, 0 times infinity. Tell me, what do you suppose 0 times infinity is equal to?
It depends.
Right, it depends. Ordinary 0 times anything is 0, but anything times infinity is infinity. So which is it going to be? Well, it depends how zero-y your 0 is and how infinite your infinity is. Depends who's got more mas poder, you know? I don't know. So like here, how about the limit as x approaches 0 of x times 1 over x? There's 0. There's infinity, because 1 over a really, really teeny tiny number is going to get you infinity. But what is that product going to be equal to? 1, right? 1, because your infinity is equally infinite as your 0 is 0-y. And so you get 1, okay? But I mean, I'm not going to beat her, I'm not going to like think of something really clever. I mean, here You tell me, what's that gonna be? This is still 0, this is still infinity, but what do I get now? 2. Yeah, so again, and then there's gonna be times when this answer is gonna be 0, or this answer is gonna be infinity. Like I said, it depends how powerful your 0 and your infinity are. Here, let me give you another indeterminate form. 1 to the infinity power.
1.
You would think,
But it depends.
you'd think 1 to the infinity power would be 1 because 1 to any power is 1, right? But what if your 1 actually isn't 1, but just slightly, ever so teeny tiny, slightly less than 1? Yeah, it's approaching 1, 0.9, 0.99, 0.999, but you've always got a number slightly less than 1. Well, what's a number slightly less than 1 to the infinity power going to equal?
Infinity.
Infinity.
Not slightly less than 1. You've done this on your calculator before,
Oh,
haven't you?
yeah.
0.9 times 0.9 times 0.9 times 0.9. Oh, what do you eventually get to?
0.
Yeah, 0. You see? So again, it depends how one-ish your 1 is and how infinite your infinity is. Here, let me give you one. The limit as x approaches infinity of x plus 1 over x to the x power. What's the limit of x plus 1 over x as x goes to infinity? 1, right? The limit of x plus 1 over x as x goes to infinity is 1. The limit of x as x goes to infinity is infinity. So do you see this as 1 to the infinity power? But you know what this ends up equaling if you were to plug this in your calculator?
5.
E.
Euler's number, E. It's E, 2.717 or whatever it is. I don't know what E is. 2.7 is as much as I've got. Okay. And of course, if I gave you this, the limit as x approaches infinity of x plus 2 over x to the x power. Do you agree that this is still 1? And this is still infinity? This is still 1 to the infinity power? You know what this ends up being? E squared. And you would get that by plugging in your calculator. So I want to tell you, our goal in using L'Hopital's rule is to deal with all the indeterminate forms and figure out what they are algebraically. Now, I'm going to tell you there's some other indeterminate forms. I'm not going to give you examples because I think you get the message. So other indeterminate forms are infinity to the 0 power, where you're going infinity to any power is infinity, but anything to the 0 power is 1. So which is it? Well, it depends. And another one is 0 to the 0 power. 0 to any power is 0, but anything to the 0 power is 1. So which is it? Well, it depends how 0-y this 0 is and how 0-like this 0 is. You see? Well, your goal in dealing with all the other indeterminate forms is you must get them looking like this. That's the key. They've got to look like 0 over 0 or infinity over infinity, because that's the only time you get to use L'Hopital's rule. No other time but 0 over 0 or infinity over infinity. So let's go for it. And the last 10 minutes of our class, I need to teach you how to deal with a couple of scenarios of these other indeterminate forms. Other indeterminate forms. Like infinity minus infinity, 0 times infinity, 1 to the infinity power, infinity to the 0 power, 0 to the 0 power must be put in the form of a fraction that is 0 over 0 or plus or minus infinity over plus or minus infinity. So that's our goal now. I'm going to give you other indeterminate forms, and we're going to put them in fraction form, and then we get to do L'Hopital's rule. Example number 1. Limit as x approaches infinity of e to the negative x rad x. As x goes to infinity, do you see that this e to the negative infinity is 0? That is, e to the negative infinity is the same as 1 over e to the positive infinity. You guys okay? E to the negative infinity is the same as 1 over e to the positive infinity, which is, has a limit of 0. So this guy is 0, but this guy is infinity. I've got 0 times infinity. I can't just stick infinity in because I get 0 times infinity, which is an indeterminate form. So I need to turn this into a fraction. One of these two guys has to go in the denominator. Who are you going to send to the denominator, this guy or that guy?
E to the negative x.
Yeah, now we're going to do the Andrew thing. E to the negative x, I'm going to make it e to the positive x in the denominator. So now I get rad x, or do you mind if I call it x to the 1/2? Because I'm going to take the derivative of it. Are you okay that this is the same as that?
Yes.
Yeah.
Good. But now, when I stick in infinity, I get infinity to the 1/2 power, which is infinity, and I get e to the infinity power, which is infinity. Hey, hey, I get to do L'Hopital's rule now. You see? I couldn't do L'Hopital's rule until I turned it into a fraction of the form 0 over 0, infinity over infinity. And so now I'm going to do L'Hopital's rule. So I get limit as x approaches infinity of 1/2 x to the negative 1/2. And this just stays e to the x. So I'm going to simplify this and hope that I don't have an indeterminate form again. Are you okay that this is going to be 2 rad x e to the x? The 2 goes in the denominator, the x to the negative 1/2 goes in the denominator. And so now when I stick in infinity, what do I get? 0. I get 1 over a hugely gigantic number, which is 0. So there it is. There's the answer. It's 0. You see? So on tonight's homework, when you're presented with something like 0 times infinity, someone's going to go in the denominator. And usually it's pretty obvious who goes in the denominator. Okay. Here's the last type of problem I've got to deal with, the indeterminate forms involving exponentials. And I'm hoping, I'm only going to have time to do like one example, and I'm hoping that's going to be good enough for you guys. Indeterminate forms involving exponents, that is 1 to the infinity power, infinity to the 0 power, 0 to the 0 power. They get their own special way of being dealt with that's a little bit complicated. This is the only really hard part of today's lesson. Here. Limit as x approaches 0 from the positive direction of x to the x power. Are you okay that this is 0 to the 0 form? This is an indeterminate form. You always want to check what form it is, right? Because sometimes they'll try to pull a fast one on you and they'll give you an exponential that isn't indeterminate, right? I mean, what if I have this? The limit as x approaches infinity of x to the x power. What's that equal to?
Infinity.
Yeah, infinity. There's nothing indeterminate about that. A million billion trillion to the million billion trillion power is a hugely gigantic number, right? There's nothing indeterminate about this. But this is indeterminate because 0 to 0, and I don't know if it's going to be 0 or 1 or something in between. You see? So here's what we're going to do. We're going to let y equal the limit. This is the process you're going to go through. Let y equal the limit, And then just like we did with logarithmic differentiation, when you want to take the derivative of something with a weird exponential, you take the log natural of both sides first. So that's coming now. That's the next step. Let y equal it, and then take the log natural of both sides of that equation. So the left side becomes the log natural of y, and the right side becomes the limit as x approaches 0 from the positive direction of the log natural of x to the x power. And then I think you know what comes next. That x goes out front. You okay with that? And now, if I plug in the 0, I get 0 times the log natural of a number really close to 0, which ends up being negative infinity. I just want to remind you the limit as x approaches 0 from the positive direction of the log natural of x ends up being negative infinity. So I've got a 0 times negative infinity situation, which means I'm going to have to do this. Someone's going to have to go in the denominator. Who would you like to go in the denominator? X, that is turning it into 1 over x and putting it in the denominator, or this guy, which would you have to turn into 1 over log natural of x to put it in the denominator? Which would you prefer to put in the denominator?
Log natural.
Well, I'll tell you, I would go with the easy one. I think it's easier to put 1 over x in the denominator than to have 1 over the log natural of x, because you're going to have to take the derivative of it eventually to use L'Hopital's rule. And I just don't like taking the derivative of 1 over the log natural of x. So I'm going to put the x in the denominator. So I get log natural of x over 1 over x. And now, as I approach 0 from the positive direction, the numerator is negative infinity and the denominator is infinity. I get to do L'Hopital's rule. So let's do it. Limit as x approaches 0 from the positive direction. The derivative of log natural of x is 1 over x. The derivative of 1 over x is negative 1 over x squared.
Mr. Shan,
Yes.
where did you get negative infinity?
The log natural of 1 is 0,
Yeah.
but then the log natural of the fractions end up being bigger and bigger negative numbers.
Oh,
You know, because I don't want to go through the process, but yeah, just do it on your calculator. Like the log natural of 0.01 is a negative number, the log natural of 0.001 is a bigger negative number, and so on. Because e to the negative whatever is going to be what gets you fractions.
yeah.
Okay. All right, well this guy, instead of dividing by negative 1 over x squared, I'm going to multiply by x squared. And so this ends up being the limit as x approaches 0 from the positive direction of negative x. Are you okay that that fraction simplifies to that? And now I get to put 0 in, and I get 0. Does that mean in my answer column I should put 0? Is that what the limit is? Is that what y is?
Yes.
Yeah. Oh, then you have to multiply by ln of y.
Never mind.
Or one
I
over
just
y.
found that the log natural of y is 0,
Yeah.
correct? I found the log natural of y is 0. So since the log natural of y equals 0, that means y is going to equal e to the 0 power, which is 1.
Wow.
So the limit is actually 1. Yes?
I know that we just separated the x, except the x differences is to the x power, and then differentiating the power.
Wait, say that again?
So could we have gone in from the x in parentheses, and then so x to x power, and then when we do the derivative of that, it's 1 times x to the x power times 1. And so that's 1 times 1 times 1, and we get 1.
No. No. Did you take the log natural of it? Or are you talking about taking the derivative of this just as is?
Yeah, when it's at the beginning.
Right, just right there?
Could you?
Well, Well, that's not gonna do any good because you only get to apply L'Hopital's rule when it's in a fraction form that's specifically 0 over 0, infinity over infinity, and you don't have that here. So getting the derivative, although it would be cool, getting the derivative isn't gonna avail you anything because L'Hopital's rule only works for 0 over 0 or infinity over infinity. Hey, can I, shoot, I really shorted us. I wish I could show you one more example, but I can't. So you're just on your own. You know, on tonight's homework, there's gonna be several problems that involve exponentials. Just remember to take the log natural of both sides, do L'Hopital's, and then get back what your y is. And good luck, you guys.